Hi, I am Dr. Shyam Sarkar. Welcome to my class. Don't forget to subscribe this channel for more updates. In this session, I will discuss top 10 MCQ question from crystal field theory. Okay, this is the advanced lecture because basic theory and basic principles I have already discussed in my previous video. If you look at these three videos, one is for crystal field theory, part 1 and part 2, and one is for 20 MCQ on CFSE. So if you go through these three video lectures, you will get basic idea about crystal field theory and you can solve from their principle all these MCQ question. Okay, so I have shared this video link in this video description. You just go through this link, then you will get basic idea about crystal field theory. So formula which I will be using in this lecture are: first one is CFSE calculation for tetrahedral system. If we need for calculation of tetrahedral system, we know if we have a electronic configuration EA T2B, that means where A and B are the number of electrons in E orbital and T2 orbital, then CFSE for tetrahedral will be A into minus 0.6 delta T plus B into 0.4 delta T. Okay, and similarly for octahedral system having configuration T2GA and EGB, here also A and B are the number of electrons in T2G orbital and EG orbital. So therefore crystal field theory stabilization energy CFSE octahedral will be equal to A into minus 0.4 delta O plus B into 0.6 delta O plus C into P. Wherever necessary, we have to consider pairing energy, and C is the number of paired electron, okay, with respect to spherical. So next formula we will be using spin only magnetic moment calculation. We know that spin only magnetic moment mu s equal to root over of n into n plus 2 bm Bohr magneton. So this is the formula we will be using. Okay, so here I will discuss about previous year solve of WB set. So 10 MCQ will be from WB set. Although these are questions from WB set, still there will be variety of questions which may come in several exams like IIT-JAM and CSIR-NET, GATE, all these type of exams. So you will get varieties of question from this lecture. Okay, so let us see the first question. The number of unpaired d electrons in the coordination complexes COF6 3- and COH2 3 plus respectively are. So four options are given. So we will solve this question and let us see. So you know that almost all cobalt 3 complexes are low spin in nature, including also cobalt H2 3 plus, except COF6 3- which is high spin. So you should remember this, because wherever you will find any question from cobalt 3 plus complexes, so you have to remember this statement. Okay, so let us see the electronic distribution. Here you can see d6 spherical distribution, and if you see in case of high spin and low spin cobalt 3 plus, so COF6 3- is high spin and COH2 3 plus is low spin. So if you see the electronic arrangement from these two complexes, you will see that in case of cobalt F6 3- there are 4 unpaired electrons, and in case of COH2 3 plus there are no unpaired electrons because this is low spin complex. So in question they asked the number of unpaired d electrons in these two complexes. So for in case of COF6 that is 4, and in case of COF6 0. So 4 0. So 4 0, it is matching with option A. So option A is the correct answer. Okay. So next question, let us see. A metal ion upon reaction with a monodentate ligand forms complexes with tetrahedral, square planar, octahedral and cubic geometries. Crystal field splitting parameters of these complexes are delta T, delta SP, delta O and delta C respectively. The correct order of splitting parameter is. So 4 different order is given. So you have to choose which order is correct for this type of complex. So there are 4 different fields given. So for this answer you have to know the relation between different systems. Okay, so different crystal systems, so there are different delta values, so you have to know the relations between them. So first we know that delta T equal to 0.45 delta O. Also we know that delta SP equal to 1.74 delta O. So there are another relation, delta C for cubic system, delta C equal to 2 delta T equal to 0.9 delta O. So if you use these relations, interrelations, so we will conclude here delta SP is greater than delta O, greater than delta C, greater than delta T. So if you see this order, so this is matching with option A. So option A is the correct answer here. Okay, so in this way you have to solve this problem. Next problem, if you see, the crystal field stabilization energy delta O of d orbital for the given metal ions is an octahedral, in an octahedral field increases in the order. So 4 orders are given. You have to identify which order is correct for this type of octahedral field. Okay, so 3 metal ions given. So for this answer you have to know, see in my basic classes I have discussed the factors on which delta O depends. So you have to know on which factor delta O depends. Okay, so here I have shared the screen. You can see the dependence of delta O with various factor related to the nature of metal. Okay, this I have detailed discussion I have given in CFT part 1. So from these also you can see that first point, if you see charge on metal ion, with increasing the charge on metal ion, delta O value increases. So here in case of cobalt 2 and cobalt 3, you can see cobalt 3 is having higher delta O value than that of cobalt 2. Okay, from the third point also we know that with increase in the principal quantum number, if you move from 3D to 4D to 5D, so principal quantum number increases and also delta O value increases. So if you remember this first point and third point, you can easily conclude that in our case the option B will be the correct answer, because in option B, see, you can see order cobalt 2 is less than cobalt 3, less than rhodium 3. So rhodium 3 will have higher delta O value compared to cobalt 3, compared to cobalt 2. So option B is correct answer here. Okay. So next question, for which of the following metal ion strongest Jahn-Teller distortion or Jahn-Teller effect is observed in an octahedral complex? Okay, so for this type of answer also you have to go through my second lecture, CFT part 2. Okay, there I have detailed discussion there with the Jahn-Teller distortion, which system will show, which system will not show. Here I will just for your convenience I have shared this chart. So here you can see strong Jahn-Teller distortion, weak Jahn-Teller distortion, and no Jahn-Teller distortion is observed with this type of D configuration. So for high spin and low spin, so these number are just D configuration, D4, D9, D7, D9, like this. So in these cases we will go one by one. So first cases titanium 3+, that is 3D1 system, and D1 system in both high spin and low spin, you can see here there are weak Jahn-Teller distortion. Okay, next let us see vanadium 3+, 3D2. So D2 also in both high spin and low spin state there are weak Jahn-Teller distortion observed. Okay, so next metal ion Mn3+, that is D4 high spin. So if you find D4 high spin in this chart, so see this is showing strong Jahn-Teller distortion. I have made in red color for your convenience. So D4 high spin is showing strong Jahn-Teller distortion. Okay, let us see the next metal ion cobalt 3+ D6 high spin. So D6 high spin, if you see, this also shows weak Jahn-Teller distortion. Okay, so among these 4 metal ions only Mn3+, that is D4 high spin system will show strong Jahn-Teller distortion. Okay, so this answer you can do from other options, other possibilities also. So see, if you see this symmetrical and asymmetrical arrangement of electrons in d orbital. So d4 high spin, if you see the electronic arrangement, T2g is symmetrically filled, but Eg is asymmetrically filled, and for this asymmetrical distribution of electron in Eg orbital shows the Jahn-Teller distortion strong. Okay, so here option C, that is Mn3 plus d4 high spin, will be the correct answer. Okay, in this way you have to solve this type of problem. So next question, see, for the complexes MnH2O whole 6 2 plus numbered as 1 and NiH2 whole 6 2 plus numbered as 2, which of the following statement is correct? So 4 different options are given with spin and orbital allowed and forbidden transitions. So first you need to know the electronic configuration of the metal ions in these two complexes. So for complex 1, that is Mn2 plus, that means 3d5 electronic configuration, and water is weak field ligand, so complexes will be high spin. So Mn2 plus, that means 3d5 high spin, that means T2g3 and Eg2. And in case of nickel 2 plus and complex 2, the electronic configuration is here T2g6 Eg2. So T2g6 Eg2, if you see, this is also high spin. So if you see this electronic configuration, so here in the first case, that means in case of complex 1, it is, see, if you see the transition from T2g to Eg level, this is spin forbidden transition, because if you see the spin selection rule here, delta S is becoming non-zero, that means this transition is not spin allowed. Also, if you see transition from d orbital to d orbital, and here in this case the Laporte is also forbidden, so this is not obeying the Laporte selection rule also. So here in this complex, both this is spin forbidden as well as orbital forbidden, that is within the same orbital transfer is not allowed according to Laporte's rule, and here dd transition is happening, that's why this is not allowed transition. So this is both spin forbidden as well as orbital forbidden for this complex 1. And if you see the second complex, here the transition occurs from T2g to Eg, and here the spin is allowed, because if you see the delta S value, so delta S value is becoming 0, that means spin allowed. So this is spin allowed transition for second complex. And if you see the Laporte selection rule, this is D to D transition, and similarly D to D transition is not allowed, this is Laporte forbidden. So if you correlate with these options given, which option is matching, if you see spin forbidden and orbital forbidden in first complex, and second complex spin allowed, orbital forbidden, so it's matching with option B. So option B is the correct answer here. Let us see the next question. The following D1 octahedral complexes are arranged in the order of their increasing frequency of maximum absorption, that is DD transition is given. Select the correct order. So here they have arranged according to their frequency of maximum absorption. Okay, so let us see how to solve this type of question. For this type of question, you have to remember spectrochemical series, which I have given in my CFT part 1 lecture in details. So from the spectrochemical series, we know the delta O value increases from Cl minus to F minus to H2O to Cn minus. So that among these 4 ligands here, so order of delta O value is like this: Cl minus is less than F minus, is less than H2O, less than Cn minus. So Cn minus is having highest delta O value and Cl minus is having lowest delta O value in these cases. So if you remember this order, and one relation you have to remember, that is, we know that delta O equal to H nu, okay, equal to E, you know, E equal to H nu, which is equivalent to delta O. So there is a direct relation between delta O and nu value. So delta O is directly proportional to nu, which is frequency. So with increasing the value of delta O, nu value also will increase. So for these 4 ligands, we can easily say the frequency order of these complexes will be TiCl6 3 minus less than TiF6 3 minus less than TiH2O6 3 plus less than TiCN6 3 minus. So if you see, this order is matching with option B. So option B is the correct answer. Okay. Next question, the value of crystal field stabilization energy of a D3 octahedral complex should be equal to. Four options are given: 0 dq, 4 dq, 6 dq and 12 dq. So this is very simple question. You can easily calculate CFSE for D3 metal octahedral metal ion. Okay. So D3 octahedral means electronic configuration T2G3 Eg0. So if you see T2G3 Eg0, that means D3 spherical field, and in octahedral also T2G3 Eg0. So CFSE will be equal to, if you put the value of A is 3, B equal to 0, C equal to 0. So CFSE becomes minus 1.2 delta O. So if you convert delta O to 10 dq value, so 1 point delta O is equivalent to minus 12 dq. So minus 12 dq is the right answer. So if you take this absolute value of CFSE, so it matching with option D. So option D is the correct answer, that is 12 dq. Okay. Next question, which of the following species is paramagnetic? This is also very simple question. If you see, the four complexes are given. So here also you will get cobalt 3 plus in all the three, B, C, D option, cobalt 3. So I already said for cobalt 3 there is a special case. So you have to remember the statement, almost all cobalt 3 complexes are low spin except COF6 3 minus, which is high spin. So COF6 3 minus is high spin and rest other complexes of cobalt 3 pluses are low spin in nature. So if you see the electronic distribution and splitting of d orbitals, so if you see the splitting of d orbitals in spherical, so this is the arrangement, and in high spin and low spin configurations of D6. Okay. So see here, COF6 3 minus high spin electronic distribution and all the other three complexes with D6 configuration having low spin. Okay. So from this you can easily say that in case of cobalt F6 3 minus there are 4 unpaired electrons, and rest complexes there are no unpaired electrons. So first one is paramagnetic and second all three complexes are diamagnetic in nature. So our answer will be option D, that is COF6 3 minus is paramagnetic in nature. Rest all these three complexes are diamagnetic. Okay. So option D is the correct answer. Next question, the expected spin only magnetic moment for FeCN6 4 minus and F6 3 minus respectively. This is also simple, very simple. So you have to calculate mu value. So spin only magnetic moment, that is already I have shared in formula section. Mu is equal to root over of n into n plus 2 Bm, where n is the number of unpaired electron. So if you see here, Fe2 plus in first complex that is 3d6 and Fe3 plus, that is d5 in the second complex. So if you see the splitting of d orbitals in both the complexes, you can easily see in case of FeCN6 4 minus, this is low spin, as Cn minus is very strong field ligand, so this complex is diamagnetic, and Fe-F6 3 minus is paramagnetic high spin complex because F minus is weak field ligand compared to Cn minus. So if you see the number of unpaired electrons here, in case of first complex that is n equal to 0, and for second complex n equal to 5. So now you put the value in the equation, you will get the mu s values for FeCN6 4 minus is 0 and mu s value for Fe-F6 3 minus is 5.9 Bm. So it's matching with option D. So option D is the correct answer. Okay. So next question, an aqueous solution of MnH2O6 2 plus is a pale pink color. The probable reason is, four options are given. One, Laporte allowed and spin forbidden. Second one is Laporte forbidden but spin allowed. Third option, both Laporte and spin allowed. And last option, both Laporte and spin forbidden. So in this case, if you see here in this complex MnH2O6 2 plus, Mn is in +2 oxidation state. That is, it has 3d5 electronic configuration. Okay. Now, and this complex is octahedral. So Mn2 2 plus, that is 3d5 is high spin in this complex, because in this is weak field ligand, water is weak field ligand, so it will be high spin complex. So electronic arrangement, if you see here 3d5, that means T2G3 Eg2. Now if you see the transition of electrons from T2G to Eg, so spin of the electron will change, so it's getting changed. So if spin changed, then see delta S value, delta S equal to plus half minus of minus half, that means is becoming 1, that is delta S not equal to 0. And we know that for spin selection rule delta S must be 0, then only the transition is allowed. So here delta S not equal to 0, that means this transition is not spin allowed. So this is spin forbidden transition. Okay. Now if you go to the Laporte selection rule, from Laporte selection rule also we can see that delta small l equal to 0. So delta L equal to 0 here. See D to D transition, L equal to 2 to 2, L equal to 2 for d orbital, so 2 minus 2 equal to 0. So delta L equal to 0 here, but from Laporte selection rule we know that delta L must be plus minus 1. So this, in this complex, Laporte transition is also not allowed. So that means this is also Laporte forbidden transition, DD transition. So in both Laporte and spin forbidden in these complexes. But you should remember here one point, that this pale pink color of this complex appears due to the vionic coupling. So during the vionic coupling, some sort of this transition, DD transition is allowed, because this is centrosymmetric molecule, octahedral complex, and in that case due to molecular vibration or vionic coupling, some sort of this type of transition is allowed, and for that this becomes in that position, it becomes partially Laporte allowed. That's why pale, that is light pink color is observed in this type of complexes. Okay, so remember this point. So if you like my explanation of these questions, you press the like button, and you can share this video with your friends. And if you are new viewers in this channel, please don't forget to subscribe this channel. Okay, so thank you so much for watching this video.